Okay, we're going to look at section 6 and section 7, and section 6 deals with free energy and temperature, and we're going to look specifically at how to calculate delta G. Now, it's good to calculate delta G based on standard conditions, but often we don't have all that information. We don't have an appendix to look all the different information up, so it's often much more useful to actually base them on temperature changes. Okay, so you have this equation here at the top. It's on your equation sheet. It says delta G equals delta H minus T delta S. The delta H component is enthalpy. The delta S component is entropy. And we usually lump that temperature in with the entropy component. So let's remember here with the text that's in black there, that delta H is, if it's positive, it's kind of an endothermic reaction. If it's negative, it's an exothermic reaction. For delta S, positive means it's more disordered. Negative means it's less disordered. Okay, and for delta G, if it's positive, it's non-spontaneous. If it's negative, it's spontaneous. So it's actually kind of a way for us to tell whether something's spontaneous or non-spontaneous. And believe it or not, it's actually an easier way to do it than to have all of the numbers in front of you and get everything out for every single delta G value, because you often don't have those. So we're going to start off with the text that's here in black. Okay, we're basically going to work through the table that's on the bottom of this section of notes. Okay, so there are two instances to tell where it's easy to tell if it's spontaneous or non-spontaneous. Okay, the first one is if delta G is negative. Okay, so just look at the black text here. Okay, if delta H is negative, that means it's exothermic. If delta S is positive, that means it's more disordered. Okay, so that means then that negative T delta S, okay, because any temperature will make it a negative. Okay. So a negative plus a negative is a negative. That's spontaneous. So anytime you have an exothermic reaction that becomes more disordered, it's going to be spontaneous. Okay. On the flip side, anytime you have an endothermic reaction, that's positive delta H, you have a negative delta S, meaning it's less disordered. Okay. That means then become your negative T delta S. Okay. Because any temperature will make it a positive. So a positive plus a positive is a positive. Okay. Anytime you have an endothermic reaction that's less disordered, it's not going to happen. That's a non-spontaneous reaction. So if it's exothermic and more disordered, it'll definitely happen. If it's endothermic and less disordered, definitely won't happen. Okay, now the problem we come into then is in the middle ground is with our temperatures, and what if I have it's exo but less, or what if I have if it's endo but less? What's that going to mean? Okay, or endo if it's more. So we're going to look at these two here that are a little bit more complicated. All right, so the one in red here, okay, it says there are two instances where it depends on the temperature to tell whether or not it is spontaneous. Okay, if delta H is negative, it's exothermic, but it's also less disordered, sometimes it'll be non and sometimes it won't be. Sometimes it'll be spontaneous. Okay, well, at a high temperature, okay, that means your delta H is going to be smaller than that T delta S portion. So think of it as two parts of an equation. You have the delta H and the T delta S. Okay? If your delta H is small, then compared to your T delta S, then overall it'll be positive. Okay? If it's the flip side, if you have a low temperature, your delta H is going to be larger than your T delta S, so it's going to be negative. Okay, for the last part, all right, if delta H is positive, that means it's endothermic. And if delta S is positive, that means it's also more disordered. So now we've got ones that are becoming more disordered, but they're also endothermic. So again, sometimes they'll be spontaneous and sometimes they won't. So if I have a high temperature, okay, delta H is actually going to be smaller than T delta S. So overall, it's going to be negative or spontaneous. So if you have a really large temperature, okay, it kind of outweighs the fact that it's endothermic. On the flip side, if you have a really low temperature, okay, that means that delta H is going to be a larger number than T delta S, so overall it's going to be positive, which means it's non-spontaneous. Okay, so basically you're just going to kind of look at whether this number here is bigger or smaller, and whether this number here is going to be bigger or smaller. Okay, if the H is bigger than the T delta S, okay, then that means that you're dealing with a positive number. If the T delta S is going to be bigger than the H, then it'll be a negative. So we'll work through these a little bit in our problems. Okay, it sounds more complicated than what it actually is. All right, so the next one we'll look at is an example. Okay, so when water as a solid goes to water as a liquid, that's an endothermic process, which means that delta H is positive, putting energy in to get your ice to melt. So as my entropy increases, okay, that means my delta S is positive, becoming more disordered. Therefore, your negative T delta S is negative because I have a positive times a negative, so the overall is negative. Now, at temperatures below 0 degrees Celsius, my delta H is going to be greater than my negative T delta S, which leads to a positive delta G. Melting of ice is not spontaneous below 0 degrees Celsius. At temperatures greater than 0 degrees Celsius, your T delta S is greater than delta H, leading to a negative delta G, and so it's spontaneous. So at some point, the T delta S component becomes too large for your delta H, or compared to your delta H, because that is a set value, that is your enthalpy value. So at some point, this value here becomes larger and actually makes it a negative number, which makes it spontaneous. But if this T is too low, then the S, even though it increases, so it's positive, if this number is too low, overall, it is still too low, which leads to a positive delta G. If it gets to be a larger number here for the T, then I'm going to have a large enough number to multiply by my entropy, which makes it overall, my delta G, be negative, which makes it spontaneous. So that's what I was getting at here with these bottom two equations. It depends now on the temperature, because that's part of this component with the S, as to then whether or not my T delta S component is positive or negative. And that's what you see right here. All right, now for the practice problem, okay. The Haber process for the production of ammonia involves the equilibrium seen below. We're going to assume that delta H naught and delta S naught for your reaction do not change with temperature for right now. Predict the direction in which the delta G for this reaction changes with increasing temperature. So we're going to assume that H and S are not going to change. Only thing we're changing is the T, and I want to see how that's going to change with my G. So I have A, okay, so I have this delta G equals delta H minus T delta S, okay. Now when we look at my S for my entropy, okay, I go from 4 moles of gas to 2 moles of gas. Since I'm going from 4 to 2, that means that my entropy is becoming more ordered. Since it is more ordered, that means it's going to be a negative. Now, if I have an increasing temperature, so I'm going to have my temperature that's going to start to go up. As my T goes up, okay, that's going to increasingly make this larger and larger. So that means that my G is going to go up, which is going to make it more positive, which makes it non-spontaneous. So my delta S is going to be negative. It's more ordered, which means overall this T delta S is positive. This whole thing here is overall as a positive. Well, as my T gets larger and larger, that makes the entire thing larger and larger. So I'm adding delta H to an increasingly larger T, which makes my G increasingly larger, which makes the that reaction non-spontaneous. If you calculate the values for delta G for the reaction at 2 temperatures, all I do is from appendix C, I just plug in my standard numbers, not the formation ones, but just the standard ones, because I have each part, okay? And it's from the previous problem, actually. So I have delta H naught from appendix C. I'm going to have negative 92.38 minus T at 298 times negative 0.198, because they all should be in kilojoules. I flipped them all, which means my delta G naught is going to be negative 33.3 kilojoules. When you look at it on the next temperature, I'm going to solve the same thing. Delta G naught is going to equal to negative 92.38 kilojoules minus my T, okay, which is 773 times 0.198 kilojoules, and I get a delta G naught of 61. So I definitely became more positive as my temperature increased. The last thing is equilibrium constant and free energy. Okay, to calculate something at non-standard conditions without the little knots, you have delta G is going to be delta G naught plus RT times the natural log of Q. Remember that Q is that equilibrium where we're at initial concentrations or pressures, and it's still the products over reactants. Okay, we're going to continue to look at the Haber process here, which deals with that making of ammonia. Okay, we're going to calculate the G for at 298 Kelvin for a mixture that consists of 1 atmosphere of nitrogen, 3 of hydrogen, and half of NH3. So I need to figure out my Q pretty much. Plug it in. Because my delta G naught, I got the previous problem was negative 33.3 kilojoules. Plus R, and this is a joules problem, so it's 8.314. Temperature is 298 Kelvin. And I need the Q. Well, Q is products over reactants. And so we're looking at the NH3 squared, which is 0.5, over the 1 times the 3 cubed, which is going to be 0.0093. So plug in here, 0093. I'm just going to solve and get negative 44.9, and these are kilojoules per mole. Let's look at the relationship between K and G. You have another equation that's on your green sheet. Remember that delta G at equilibrium is 0. That's when Q equals K. So I get this equation that looks like this. Delta G naught is going to be the same thing or equal to as negative RT times the natural log of K. K is only going to be equal to, if I solve for K, E to the negative G naught over RT. Again, it's the same R with 8.314. So we're just remembering that G can be 0, so I'm getting rid of the, or when G is 0 at equilibrium, which means then I can put the Q and the K in flip-flop, and I can just plug in 0 and K, and this is what I get. Then when I plug in all these numbers for my problem here, it says using the standard for energy formation, we're going to calculate the equilibrium constant K at the same temperature. I have the values for delta G naught that we got from a few problems ago. So I'm just going to have K equal to E to the negative G naught over RT. K is E to the negative 3,000 or 33,300 divided by 8.314 times 298. And this whole business right here is 13.4. So I have E to the 13.4, which is 7 times 10 to the 5th is my equilibrium constant.